start recording this virtual session. This is our first Earth Science virtual session. Hopefully we'll be growing in size every week because we do have a lot more than 4 people in the class. Regardless, when you attend a virtual session, looks like everyone's doing this so far, your camera needs to be on. You need to participate and be respectful, right? That's it. I'm going to try to make these sessions really useful for you in terms of giving you difficult content or important content. Some of the sessions will be collaborative where we talk about things or talk about articles or other ideas going on in science. And in a lot of them, we will do our discussion-based assessments that are required for the class. Now, you don't have to have your face centered in the camera the whole time, right? I have no problem with you tilting the camera away from you slightly. That's totally fine. But I just want to make sure that you're there and you don't just log into my session and then walk away from your computer, mostly because I already know this stuff, right? So I'm here for you and to help you understand this class a little bit better. So in today's session, we're going to start with a warm-up question. So I want you to take a few moments to think about this question and either type your answer in the chat or you can speak your answer into the session, right? You have a choice. I'm totally fine with you using the chat if that's where you feel more comfortable. But what is the difference between a theory and a law? So take a second to think about that. Pop an answer into the chat. You could talk about maybe just one of those things, both of those things. What is the difference between a theory and a law? Keep in mind, you're welcome to use your resources right now. If you're not sure, you could be looking up definitions for this, coming up with an idea for what the difference is. But we'll patiently wait here until we get a couple of answers. Awesome. Thanks, Alina, for being the first one to put an answer forward here. I think a theory is when someone is someone's thought or thinking, but a law is a thing that you have to follow. Okay, that's interesting. Abby tells us that a theory is something scientists have developed through experimentation. It is subject to change if new experiments or evidence arise. A law is an explanation of an occurrence in nature and doesn't change. Excellent. So I'm just going to highlight a couple things here that Abby said that are super important, right? A law is something that nothing can really disprove, right? So for example, usually gravity is referred to as a law. We all know gravity exists, right? We're all not floating away from Earth right now, thankfully. So we know gravity's there, right? And there's been thousands and thousands of experiments over hundreds of years to prove that. And no one's ever been able to disprove that, right? Whereas a theory, as Abby stated, is something that there has been a lot of research on. There's a lot of experiments that say it seems like this is happening, right? But we can't quite prove it 100%. And a lot of times theories will be things that are, you know, back in time, like how the Earth formed. Well, was anyone there to see the Earth forming? No, right? So we can experiment all day. We can have a million ideas about how that might have happened. However, we'll never know for sure. Unless we invent a time machine, then we might know for sure, right? So theories can change, and sometimes they do. I like how Jillian added on that a theory is an explanation of observed data or observational data, and a law is an obvious fact. Yeah. So a lot of times we get these words kind of thrown around with the word fact, right? And it can be a little confusing. So just keep in mind that even if it is a theory, there's still a ton of evidence behind it, right? It's not like somebody just sat around and said, you know what? I think life came from another planet, and everyone went, cool. We don't need any experiments to prove that. Let's go with it, right? People would have experimented, which, by the way, that is a theory of how life may have started on Earth, because they found meteors with life inside of them, right? So it would make sense that life could have traveled to Earth from that. So all theories have some kind of evidence behind them. Okay, moving on. Before I just continue ranting about theories, I like to rant sometimes about science definitions. What we're going to do today is we're going to talk about measurement, right? That's pretty much the most important thing from this first module. We're going to describe methods to measure the mass and the volume of different types of objects. And for a lot of us, this is probably a review, right? Most likely in every science class you've ever taken, you've done some kind of how to measure, done measuring possibly, right? It's a little different in the virtual world, but we still have to talk about it because it's important to know. So I'm also going to be linking some resources here for how to take Cornell notes. You do not have to take Cornell notes for this class necessarily, but I want you taking notes. There are notes checks. So some of you who've been looking ahead might have even noticed if you go in to the course in Canvas and you go to modules, coming up at the end of each module, there will be a notes check. Whoops, I just passed it. As you can tell, my Canvas sometimes scrolls a little bit too much. So beginning with science note check. I have this assignment locked until September 20th. So that means you can't see it. You can see that the assignment exists, but you can't see the instructions behind the assignment, right? Inside the assignment, I will tell you a specific lesson that I'd like to see notes from. You're only going to have 24 hours to turn them in. So if you've been taking notes the whole time like you're supposed to be, that's super easy. You're going to open the assignment. You're going to go, oh, she wants to see notes from matter and energy. Here's my notes from that. Done. If you're somebody who doesn't really take notes, or maybe you kind of took notes, you're still going to have 24 hours to either take notes and pretend that you did it the first time, right? Or modify your notes or add to them or whatever you need to do. So make sure you keep an eye on those. There's one for each module, and it's only going to be visible for 24 hours. And if you don't do it, that's it, right? It passes. It's not worth a ton of points. So even if you never turned notes in for this class, you could still get an A, right? So don't be super discouraged. Oh, I didn't turn it in, I'm going to fail. No, right? But notes are important for many reasons. One reason being you can use your notes on the exam in this class, right? Why would you not take notes? It's going to be really hard on the exam if you're trying to go back through every single lesson and find the answer to something. If you have notes where you have the key ideas summarized, it's going to go a lot faster for you. So keep that in mind. Those notes checks exist, and they are going to happen once per module. The first one is going to be September 20th, which is next week. I believe I asked for notes on matter and energy. So if you haven't done that lesson yet, take notes on that. It might be atomic structures and forces, but it's one of those lessons. I don't want to give you guys too many hints. Okay, so back to this. So anyway, I'm going to post this PowerPoint probably tomorrow morning in the course with a link to this video, and there will be links here. If you're not sure how to take notes or you want to take Cornell notes, there's a bunch of ways to learn how to do that from this slide. Okay, so today we're going to be answering the question, how can we measure the mass and volume of objects? Super easy sounding question. You could probably list like 18 ways right now if I asked you to. So let's talk about why we measure things, right? It allows us to quantify or assign numbers to physical objects. And in this class, right, we have a lot of different types of measurements. For the most part, we're going to see mass, temperature, and volume, right? You might also see quantity, which would be like how many of something you have. Circumference probably looks familiar to you from math. But really, the reason that we measure in science is so that we have actual values in order to justify our theories and laws, right? If you have measurements, it's much more believable to say, oh, this is impacting the world, this is impacting something else, because here is the data to support my thinking. Right, so math is very important in this class. We won't be doing a ton of math. We'll mostly just be looking at data and analyzing data as a class. Physical properties, right? This was another vocab term that was thrown into this lesson. Physical properties are anything that can be described or observed about an object. Right, so measurement is an example of that. Further examples would be the color, the size, the shape, the mass, the density. Does anybody happen to remember from math or another science class what density actually is? You might even think, how would you describe density to somebody else? If you're saying something is dense, what does that mean? Yeah, maybe something is thick. Sure, right? So there is a formula. Density is going to be equal to mass divided by volume. You might be having some flashbacks to that now that I just mentioned it there. Solidness is a good guess, right? It's how much mass is compacted into a certain volume. So you might think, about a brick in someone's house. That's pretty dense, right? There's a lot of mass in a small amount of volume. It weighs a lot, and it's pretty small. Whereas if you think about a piece of styrofoam, right, it doesn't have much density. There's not a lot of mass in that same amount of volume that there would be in a brick. So density is something that is a physical property because it doesn't change no matter how big or small the sample is, right? If we took the density of the tiniest piece of a brick, it would be the same as if we took the density of a huge piece of the brick. It's something that doesn't change unless you physically change that object, right? And then it would be something else. So density is an important one. Mass versus weight. This is another misconception in science, right? These things are not the same thing. I'll catch myself this year probably doing this. You guys might as well. Sometimes we just say weight when we mean mass, right? We say, oh, find the weight of the object. Find the weight of that. This weighs more than this, right? Weight is impacting this. Especially when we start thinking about like planets and things out in space, we might be thinking about the weight of something, right? But the weight really is actually the impact of gravity on your mass. So you would actually weigh less on the moon than you would here, right? You would also weigh less if you go up on top of a mountain. It's not going to be a ton, but let's say you go visit Denver, Colorado. You're going to weigh less in Denver, Colorado than you do here because you are at a higher altitude, right? There's less gravity impacting you. However, your mass didn't change, right? Unless you happen to actually lose physical mass off your body. Like let's say we cut your arm off. All right, your mass changed, right? But otherwise, your weight is only going to really tell you something based on where you are. So a lot of times we interchange these words because they are the same value in our specific location. But if somebody in another country or another location is to take the mass of an object, their mass should be the same as ours, but their weight might be different, which I hope that makes sense. A lot of you guys might have been to museums or other places where you can stand on scales that tell you how much you would weigh on Mars or on Jupiter or on other planets and things like that, right? It's the same concept. Gravity is impacting your mass, rather than just the amount of mass that you have. Okay, so I basically already kind of did this because I get really excited about this one. But are mass and weight always the same? So the answer is no, right? They're not. And they can be the same though. So I kind of just said this, but let's take a second here to summarize and actually write a couple little points about this. So what is an example, or when is a time that mass and weight would be the same? This is kind of a hard one. I think it's easier to think of when they wouldn't be the same. But what do you guys think? When would they be the same, mass and weight? Moon or Earth? Well, when you take them in the same place. Yeah, so when they are measured in the same exact location, right? So in that case, your mass in Gresham equals your weight in Gresham. Okay. But Geo's kind of getting at when there might be a difference, right? Your mass on Earth is the same as your mass on the moon, but your weight is different. So mass never changes, right? Again, unless you physically take mass away, right? Or if you do lose weight, you technically are losing mass as well. But your weight will be different depending on where you are. So that's pretty cool. You know, if you know anyone who's like obsessed with how much they weigh, right? It fluctuates a lot, even just day to day when you're in the same spot. But some people get so excited because they'll go on vacation and they'll think, oh, look, I lost 3 pounds. And really, they just are at a different altitude. And so they have the same amount of mass. It just seems like they weigh less. It can be pretty tricky. Okay, so the reason that I'm emphasizing this is because there is a question about this on the quiz and the module exam for this unit. All right. So now you guys are going to tell me, what tool would we use to measure the mass of a liquid? How would we do that? If we have a sample of water and we want to find the mass. Okay, Geo says beaker. Good, that's part of it. So what? I just pour the water in the beaker and that tells me the mass. And you may be thinking, I don't know what this object is called, right? Maybe you're thinking that some kind of scale, right? A scale is the correct answer. A lot of times we use this thing right here, the triple beam balance. You guys might have seen one of those before. You can also use a digital scale, right? Much like you would use to weigh yourself or find the mass of yourself. But a triple beam balance is pretty common to use in this class. So in order to find the mass of a liquid, the hard thing about it is liquids don't stay in one place, right? That's part of their properties. They spread out. So you do need a container. So Geo's right that we would need a beaker. right? However, we don't want the mass of the beaker. We only want the mass of the liquid. So in this case, we would need to find the mass of a beaker plus the liquid, and then we would subtract the mass of the beaker. So we would take our empty beaker or cup or whatever we're going to use, we would place it on the scale. Maybe we find out that it weighs 10 grams. Once we pour our liquid in, we see that it weighs 50 grams. We would then subtract out the mass of our beaker and get 40 grams as our total mass of the liquid, right? So keep that in mind. There's nothing wrong with placing objects or liquids or gases in a container in order to find their mass. What about the mass of a sphere? This one should be a little easier. Think about if you have a basketball and we want to find the mass of it, what will we do? Any ideas for how we could find the mass of a sphere? All right, guys, you got to talk to me. If I don't have anyone talking to me, I'm just going to end the session because I already know the answer to all of these, right? This is for you. And if you're having a hard time thinking of how to find the mass of something, that tells me that we need to be going through this. When we use a formula, that's a good guess. Maybe we would just place it on a scale, right? This one's kind of obvious. Place on a scale. Could be a triple beam balance, could be a digital scale, right? If it's rolling around, we might have to do the same concept as we would with the liquid. You could put it inside a container, right? And take away the mass of the container if you needed to. What about the mass of a wood block? Yeah, same thing. Place it on a scale, right? Some of these are obvious. The wood block will be the easiest one, right? It's not going to move. You're just going to set it down. It's going to tell you the mass. That's it. And you record it. That one's the easiest. The hardest things to measure mass for are liquid, right? Also, potentially strangely shaped objects that roll or bounce, right? That can be really complex. Okay, now volume. Gio, we might want to be thinking about what you said here about a formula. Liquid volume is in a beaker, exactly, right? Think about a measuring cup that you might use at your house. A beaker is the same thing. You pour a liquid in, it tells you it's 100 milliliters. It's 3 cups, right? It tells you the volume of the liquid. So you just use a beaker or glassware, I'll say, because there's a bunch of other kinds you could use as well. What about the volume of a sphere? Yeah, a formula. Good. We're just going to say formula. We don't have to actually write it out, right? But I think it's like volume equals 4/3 pi r cubed, something like that. I don't even have a pi symbol, so I will not even bother. But yeah, we use a formula. And then what about the volume of a block? A formula, right? Again, that would be length times width times height, right? We would just multiply all the sides. Now, we could also find the volume using a liquid, where you can actually drop an object into something and see how much the volume increases in the liquid. So you might have experienced this if you've ever taken a bath, right? Or you've gotten in a pool. Once people get in the pool, the water level rises because now your volume is being accommodated in the water. So that's another way we can do it. That's not as accurate, right? Usually you only do that for an irregularly shaped object. So like if I said, find the volume of yourself. Well, it's kind of hard to measure yourself and find the volume, right? In fact, that might be a good extra credit challenge, finding the volume of yourself, because it's pretty challenging to do. So sometimes we can use a liquid to find the volume, but for the most part, it's a formula-based thing, or we use a beaker for liquids. Okay. So again, here's just kind of what these things look like. And the thing I just talked about, we'll look at here with this T-Rex. But basically, graduated cylinder is right here. It's really similar to a beaker. It's just a tall, skinny plastic or glass container, right? It has markings on it. It'll tell you the volume of a liquid. You can also use it to measure the mass of a liquid by using it to place the liquid on a scale. Here we have the most common scale that you see in science, the triple beam balance. Type a 1 in the chat if you've ever gotten to use a triple beam balance in your life. Yeah, a lot of us have used one, right? It's kind of fun. It's pretty hard though. They're not very accurate, which you may have noticed. It kind of just wobbles up and down, up and down. You have to be very patient, right? And then over here on the right of the slide, we see a T-Rex, right? He's an irregularly shaped object. What formula would we use to find the volume? Ooh, I don't know. It would be hard. We'd have to break him up into a ton of little rectangles, right? That would take forever. So in order to find the volume, we just fill a graduated cylinder up with water. We look at where the water starts. We take our T-Rex, we plop him in, right? He sinks, and then the water rises. So based on what you see in this picture, what is the volume of T-Rex? Five and a half, 5. Well, let's see, where are we starting, right? We got to think about what these little tiny marks mean. We have 1, 2, 3, 4, 5, 6. In between a 5 and a 6, we have 1, 2, 3, 4 smaller lines. So that tells me that these have to be 0.2. So this is 5, 5.2, 5.4, 5.6, 5.8, and then 6. So T-Rex does go up to, it looks like 5.6 once he's in the water. However, did he start at 0? No. Right? So we have to subtract out this initial water. Otherwise, we're going to say that the volume of T-Rex is way bigger than it is. So in this case, we would actually take our final number, 5.6, and we would subtract 4.8, which is where our T-Rex started. And we would find out, excellent, Geo, that our volume of T-Rex is 0.8. Now, you may have noticed I was reading this on the bottom of the water, right? Water curves in containers and it goes up towards the sides. You might even have seen this when you pour water into a cup. We always read at the bottom of the water. So if we read at the top, in this case, you would get the same answer. But we read at the bottom of that curve on the water. So T-Rex is 0.8. We don't know what the units are, so we'll just say units, right? Could be liters, could be milliliters, some kind of volume unit. So this is a way that we can find the volume of something that's irregularly shaped, which I really wish I could have done in math, right? Have you guys had any of those math questions yet where you have to break everything up into like 17 triangles to find the area or the volume, right? It gets really, really complicated. It would be nice if you could just drop something in water and it tells you the volume. All right, so moving on. Error, right? This is something that also is always present in science. And a lot of times people think that it sounds bad, right? We think, oh no, you made an error, that's bad. It's not, right? It's always there, it's always existing. It's not necessarily a bad thing. It really just means that we can't get accurate enough measurements to be 100% confident in everything that we do, right? So for example, when we were looking at T-Rex, over here, right, and I read this first water marking as 4.8, usually I would also take a guess. I might think it's 4.82, 4.84, something like that, right? You might have seen 4.88. You might have seen 4.80, right? So depending on how we view that water, we might have gotten a slightly different measurement. Now, is that going to matter? Probably not. But it does make it so that we can't be 100% accurate. We might find out that the true volume of T-Rex was 0.825431.8 for 10, 10, 10, 10, 10, you know, a bunch of numbers after that, where we wouldn't be able to understand that from looking at this water, right? The other thing I want you to think about is if you take your pencil, right, and I ask you to drop it on your table or floor the exact same way 10 times in a row, can you do it? Gio's like, I don't even have to try. No, you can't, right? Even if you get it to the same height every single time and you drop it with the same release of your hand, every time your pencil hits the floor, tiny atoms of it fall off. So it's not even the same pencil when it goes back up in the air, right? That's the kind of stuff we're talking about here. It's like error that you don't even want to think about because it seems crazy, but it's true, right? Your pencil, once it touches something, is never the same pencil that it was before. So it's impossible to do things the exact same way multiple times. And that's what we try to do in science. We try to get as close to doing that as possible, right? And then there's other kind of error, like you just messed up, right? You spilled something, your T-Rex got run over by a car, so we got kind of flattened, right? That would make your experiment have some human error as well. But keep in mind, there's just natural error that's always there that we can't really do anything about. So if I ever ask you in the future of this class, were there any errors in your experiment? The answer is yes, 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 yes. There's always error, right? You may not have made any mistakes, but error still exists. Okay. We're done with this lesson, if you can believe it. So I want you guys to try to summarize this lesson in 20 words. Do you think we can do it? Do you guys want to do it together? Type a 1 in the chat if you want to try to do this together. Okay. Helena's like 1, yes, yes, yes. Okay, cool. So who wants to start us off? What should we say to start off our summary? Hello, guys. Haha. How does that start off our summary? I like it, though. You're trying to be casual. What if we say something about measurement, right? We discussed, like that, we discussed measurement, mass, oops, volume. Ooh, mass versus weight. I like that. We discussed measurement, mass versus weight, volume, and how it is used in science. Did we even need 20 words? I don't think so. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, anything else that we would want to add? What about error? Yeah, error. Plus, we'll just say plus, error is always there. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 words. We'll go with it. Right? So as you leave this lesson, make sure you know what all those words mean. Are you confident you know what measuring is? Are you confident you know the difference between mass and weight? Do you know what volume is? Do you know how we would calculate that? Do you know how we would calculate mass? Do you know why and how we use those things in science? And then do you know what error is and why it's always there? right? This is a good practice you can use for yourself when you go through these lessons in Canvas. Try to summarize the whole lesson in 20 words, right? And if you have a really hard time with it, that means you probably need to go back in the lesson and look at what was happening, right? And if you have a hard time keeping it to 20 words, that means that you're putting too much information, right? So this is a really good strategy, a way to study even. You could go through each lesson and see, okay, did I really know what was going on here? Because can I say what happened in 20 words? Okay, so you are going to be getting a code word. I am going to write it in the chat. This code word which you will not share with anyone else in the class, is your reward for coming to the virtual session today. You can include that on your measurement quiz or any other assignment in Module 1, and you will get 5 points added. So write it down somewhere that you will remember, right? This is totally up to you. You can even save it if you want. I had people last year who saved all of their extra credit code words and put it on their final exam and ended up getting 100 on their final exam because of all of the code words that they have. Can you email it to me? Yes. So you can send me an email. Miss Jamie, I would like to add my points to this assignment, especially if I've already graded it or you've already turned it in. Can you use it on every assignment? No, but every virtual session you attend, you will be getting a code word, right? So you can use them however you'd like, right? My suggestion is use it on a quiz or an assignment that's really hard for you so that you can help boost your points up a little bit. Yeah, Alina, you could totally save them for the final. No reason, right? Now, does that mean you can just click random stuff and be like, I want to use my points? No, right? Like actually try to. But it'll help you with a little buffer. So make sure you've written down that code word, which I can't say, and the people who are watching this recorded can't see because they can't see the chat. And otherwise, that was it. We will have a virtual session next week. We will be doing the DBA in the next virtual session. If you're not sure what a DBA is, that's a discussion-based assessment. That's just a little conversation we're going to have to make sure that we understand the main points of this first module. One of the questions will be on measurement. Where do you turn in the exit slip? You don't have to turn it in. It's just the code word, and if you choose not to use it, then you choose not to use it, right? But that code word will give you 5 extra points on a quiz, test, or assignment. Yeah, sometimes we will have a real thing you have to turn in, right? But this week, there's not something to turn in. I feel like you guys have a lot of stuff to do. The beginning of the year is like hitting you in the face with stuff. At least that's how I feel. So, you know, take your time to get oriented to the class. Use the code word to help you get some more points. And otherwise, make sure you email me if you have any questions, you have suggestions, you have concerns, anything like that. Please let me know. And otherwise, I will see you guys next week.